Time travel. The very phrase sparks our imagination. We yearn to witness pivotal moments in history, to glimpse the distant future, or perhaps even to correct past mistakes. Stories of time travel have enthralled audiences across generations. Physicists and mathematicians are grappling with the complexities of space-time, searching for loopholes in the laws of physics that might allow for temporal manipulation. Our journey begins with Albert Einstein, the brilliant mind who revolutionized our understanding of space and time. His equations suggest that time is not absolute, but rather a fluid dimension interwoven with space itself. Wormholes, in essence, are shortcuts through space-time. Picture them as tunnels connecting two distant points in the cosmos, allowing travelers to bypass the vast distances that separate them. The immense gravitational pull of black holes warps time to an extreme degree, potentially offering a one-way ticket to the future. Our everyday experience tells us that time marches forward at a steady pace. But Einstein's theory of relativity throws this intuitive understanding into disarray. It reveals that time is not absolute but rather relative, dependent on the observer's frame of reference. This phenomenon, known as time dilation, becomes more pronounced as an object approaches the speed of light. Time dilation isn't just a theoretical concept, it has been experimentally verified. These experiments demonstrate that time is not a rigid, unchanging entity. Imagine folding a piece of paper in half so that two distant points touch. This, in essence, is the concept behind a wormhole, a theoretical tunnel connecting two separate regions of space-time. These cosmic shortcuts, predicted by Einstein's equations, could potentially allow for travel over vast distances. Creating and stabilizing a wormhole would require exotic matter with negative mass-energy density, a concept that lies firmly in the realm of speculation. Despite these challenges, the concept of wormholes continues to captivate the imaginations of scientists and science fiction enthusiasts alike. The theoretical existence of wormholes presents a mind-boggling possibility, a cosmic shortcut, a tunnel through the very fabric of space-time. One of the primary challenges lies in the stability of wormholes. Stabilizing a wormhole would likely require exotic matter, a hypothetical substance with negative mass-energy density. Entering a wormhole at a particular point in space-time doesn't guarantee your arrival at a specific destination. The intricate topology of space-time, warped and folded by gravity, could lead to unpredictable outcomes. Black holes, those enigmatic cosmic objects where gravity reigns supreme, offer another potential avenue for time travel, albeit a one-way trip to the future. As you approach a black hole, time itself begins to slow down, a consequence of Einstein's theory of general relativity. Imagine a spacecraft hovering near the event horizon of a supermassive black hole. For every hour that passes on the spacecraft, years, decades, or even centuries could pass in the outside universe. However, this journey to the future comes at a steep price. Wormholes, those captivating wrinkles in the fabric of space-time, tantalize us with the possibility of bridging vast cosmic distances, even venturing into different realms of time. Imagine a shortcut, a tunnel through the very essence of existence, connecting distant points in the universe, or perhaps even different universes altogether. Wormholes, in theory, are like tunnels through this warped fabric, connecting distant regions through a shortcut. But wormholes are more than just intriguing theoretical constructs. They are active areas of research in theoretical physics, pushing the boundaries of our understanding of the universe and its hidden possibilities. Our everyday experience suggests that space and time are separate and unchanging entities. But Einstein's theory of relativity shattered this classical view, revealing that space and time are intimately intertwined, forming a unified fabric, space-time. Imagine a vast, flexible sheet warped and curved by the presence of massive objects. This sheet represents space-time, and the curves represent gravity. Wormholes, in this context, are like tunnels through the fabric of space-time, connecting distant regions through a shortcut. The theoretical existence of wormholes is tantalizing, but their creation and stability present formidable challenges. One of the biggest hurdles is the requirement for exotic matter, a hypothetical substance with bizarre properties, including negative mass energy density. Exotic matter with its negative gravity could counteract this inward pull, stabilizing the wormhole and preventing it from collapsing. However, the existence of exotic matter remains purely theoretical. Scientists have yet to find any evidence of its existence in the universe. Despite the theoretical hurdles and the lack of empirical evidence, the concept of wormholes continues to captivate our imaginations, fueling dreams of interstellar travel and even time travel. Stepping through a wormhole would be like passing through a looking glass, entering a realm where the familiar laws of physics might bend or break. Imagine a network of wormholes connecting distant corners of the universe, like cosmic highways bypassing the limitations of conventional space travel. But the implications of wormhole travel extend far beyond mere exploration. The ability to manipulate spacetime in this way raises profound philosophical questions about the nature of causality, free will, and the very fabric of reality. Time travel, with its tantalizing promise of venturing into the past or future, inevitably confronts us with a thicket of paradoxes, challenging our fundamental understanding of cause and effect. The most famous of these, the grandfather paradox, exposes the potential absurdities that arise when we tamper with the delicate tapestry of time. Imagine, if you will, a daring time traveler, fueled by a reckless curiosity or perhaps a misguided desire to alter the past. This intrepid explorer ventures back in time, arriving in an era long before their own birth. Through a series of improbable yet strangely inevitable events, our time traveler finds themselves face to face with their own grandfather. The grandfather paradox, while a thought experiment, highlights a fundamental problem with time travel: the violation of causality. Causality, the principle that every effect has a cause and that events unfold in a specific order, underpins our understanding of the universe and our place within it. If we could travel back in time and alter the past, we would essentially be breaking the chain of causality, creating contradictions and paradoxes that defy logic and reason. Imagine a world where effects could precede their causes, where the future could influence the past. Every action taken in the past, no matter how small, could have unforeseen and potentially catastrophic consequences in the future. The grandfather paradox paints a dramatic picture of the potential dangers of altering the past. But even seemingly innocuous actions could have far-reaching consequences, creating ripples that spread through the river of time, altering the course of events in subtle yet profound ways. Imagine a time traveler venturing back in time merely to observe a historical event, vowing not to interfere in any way. However, their mere presence, even if unnoticed by those around them, could have unintended consequences. A stray cough, a dropped object, or even a footprint in the dust could disrupt the delicate balance of events, leading to a future vastly different from the one they remember. This concept, often referred to as the butterfly effect, suggests that even the smallest actions can have significant and unpredictable consequences over time. A butterfly flapping its wings in Brazil, the saying goes, could set off a chain of events that eventually leads to a hurricane in Florida. In the context of time travel, the butterfly effect takes on a whole new level of complexity. A seemingly insignificant action in the past could cascade through time, creating ripples that grow into tidal waves, altering the course of history and shaping the destiny of countless lives. The relentless march of time, always moving forward, is a fundamental aspect of our experience. We remember the past, but we cannot change it. We anticipate the future, but it remains uncertain. This unidirectional flow of time, often referred to as the arrow of time, is intimately connected to the concept of entropy. Entropy, in simple terms, is a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy always increases over time in a closed system. This means that the universe as a whole is constantly moving towards a state of greater disorder. The arrow of time and the increase of entropy seem inextricably linked. It is the increase in entropy that gives time its direction, preventing us from spontaneously reassembling a broken egg or unringing a bell. Time travel, however, throws a wrench into this seemingly inviolable law. If we could travel back in time, we would essentially be reversing the arrow of time, at least locally. This reversal of time's arrow could have profound implications for entropy, potentially leading to a decrease in disorder, a violation of the second law of thermodynamics. The grandfather paradox challenges time travel enthusiasts with its logical inconsistencies. How can we reconcile time travel with causality? One solution is the many worlds interpretation. Time travel creates new branches, not altering the original timeline. This dissolves the paradox, preserving causality. The many worlds interpretation presents a liberating perspective on time travel. Imagine a universe of infinite possibilities where every decision spawns a new branch of reality. Our lives are a single thread in an intricate tapestry of countless possibilities. The universe we perceive is one of many coexisting realities. Time travel becomes a journey across these parallel universes. A time traveler might find themselves in a different version of history. They might encounter alternate versions of themselves. The implications are staggering. Imagine exploring a universe where you made different choices. The many worlds interpretation opens up limitless exploration. The many worlds interpretation offers a compelling solution to the grandfather paradox. But another approach, the Novikov self-consistency principle, proposes that the laws of physics prevent paradoxes. Named after physicist Igor Novikov, it suggests any action by a time traveler must be consistent with history. The universe self-corrects, ensuring the past leads to the present. This leads to causal loops, where past and future events are intertwined. Imagine a time traveler giving their younger self an invention they will later use. The invention is both a product of the future and a cause of its own existence. The quantum realm, with its inherent uncertainties and probabilistic nature, adds complexity to the mysteries of time and causality. Events in the quantum world do not unfold predictably. Instead, they are governed by probabilities where multiple outcomes are possible. Observation determines which outcome manifests. Heisenberg's uncertainty principle suggests the past is a superposition of possibilities. Time travel might involve navigating a shifting landscape of quantum possibilities. Our expedition through the cosmos of time travel has taken us from the mind-bending implications of Einstein's relativity to the perplexing paradoxes that arise when we dare to tamper with the fabric of time. We've peered through the theoretical looking glass of wormholes, those cosmic shortcuts that might bridge distant realms of space and time, and we've grappled with the philosophical dilemmas posed by the grandfather paradox, a stark reminder that altering the past could unravel the very fabric of our existence. The allure of time travel, the dream of witnessing firsthand the grandeur of bygone eras, or glimpsing the uncharted territories of the future, continues to captivate our imaginations. Yet, as we've seen, the pursuit of this dream is fraught with challenges, both scientific and philosophical. The laws of physics, as we currently understand them, present formidable obstacles, from the immense energies required to warp space-time to the potential for paradoxical consequences that could unravel the causal fabric of the universe. But the very act of exploring these challenges, of pushing the boundaries of our understanding, is at the heart of scientific inquiry. The pursuit of time travel, even if it remains forever out of reach, forces us to confront fundamental questions about the nature of time, causality, and the limits of human knowledge. As we stand at the precipice of the unknown, gazing out at the vast cosmic ocean of possibilities, we are reminded that the universe is far stranger and more wondrous than we can possibly imagine. Einstein's theory of relativity has shown us that time is not rigid but fluid, interwoven with space. The concept of time travel, once science fiction, now spurs scientific inquiry. The cosmos, with its endless possibilities, beckons us to explore and embrace the unknown, to never cease wondering about the true nature of time, space, and reality.